Okay, so this is a supplemental lecture. We're going to go through a few of the checkpoints, though you can feel free to just look through the notes that we'll post up on Moodle. Now, the first thing I wanted to go over was what were the goals? I mean, I started with the defining question of like, how do we represent something, or how do we describe something that's doubling all the time? When we look at the specific learning objectives that we want you to get out of this, we want you to be able to calculate the parameters of an exponential function that passes through two data points. So reading from a graph. Look at the difference between the average and relative rate of change, and how you end up calculating or estimating the relative rate of change over a given interval. Remember that is only, just like with a linear function, where the average rate of change is only exact for a perfect linear function, the relative rate of change is only exact for an exponential function, unless you get into, well, calculus later on when we get into limits. So we'll find out how to do those properly later. We have not done fitting an exponential function to a set of data points, and so this is something where you can try adjusting different parameters to try to best fit a graph. Determine if an exponential function defines growth and decay, which is at the end of that last checkpoint, and determine if a set of data might correspond to an exponential function. I mean, does it follow one of these three forms that you have down here? Does it keep increasing by a constant relative rate? And the stretch goal being switching back and forth between all three versions, because they tell you different things. You'll see them depending on context. You might see one version more frequently than another, and then understanding what continuous rate versus a discrete rate is really important. So for checkpoint 1, this was looking at how we get things from a graph. So the first thing, if we were to have an exponential graph that started at 10, as you can see by comparing the two, all you do is multiply everything times 10. And to see how this is reflected in the equation, you can just look at the defining equation. And so this one, I think, was the 2 to the x. So this is y is equal to 2 to the x. And this would be y is equal to 10 multiplied by 2 to the x. And what does the graph tell you without doing any calculations? So without taking two different points, what I can do is zoom in here and recognize, hey, its y-intercept is exactly my initial population. So I can just read that straight from the graph, and I can get my parameter a, y naught, whatever they end up calling it. So you can get this from looking at that. Now, how would you determine the base of the exponential, assuming it's in the form f of x is equal to f0 times b to the x? Well, let's say we didn't know that this was, here, let's see if I can make this, whatever. Let's just say we didn't know what that was, that 2, and we wanted to find out. We were able to read from the graph what this initial population was. What I can try to do is to read from a data point from the graph. Let's say 3, so 1, 2, 3, and this looks like, what is it, 50, 60, 70, 80, 80. So we have 3 and 80. Well, then right away, we can say, okay, I've got y is equal to 10 times b to the x. We know y is equal to 10 times b to the 3. Oh, sorry, that 80 is equal to 10 times b to the 3. And so divide both sides by 10. I get 8 is equal to b cubed. And so I can get that b is equal to the cubed root of 8, which is equal to 2. So using that extra data point, we can find that out. Now, if we didn't have that initial one, you can solve it using two data points, either following through that algebra, doing some fun things by where you divide one equation by the other. There's a few different ways to get to this, but yeah, using that equation and recognizing that the coefficient is that initial population is key. Okay, now find the relative rate of change per year by choosing 1 year to be so many days, using that formula in terms of like 1% per day to help you figure out what it is per year. And we want delta x measured in years, and compare the average rate of change from year 1 to year 2 to the average rate of change found by the end of year 1. Repeat this with relative rate of change. So actually, why don't I call it x instead of y, because that's kind of confusing. I mean, you should be okay with having a independent variable that I label as y. It's just good practice, but for now we'll be representing this as I is equal to 100 times b to the x, where x is measured in years. Now, I've started by making out a table, and by using my calculator and this original formula where it was done in days, I was able to find out, well, at 1 year, I had about almost $4,000. And at 2 years, I had $143,000. This is a great investment. Now, I then made a table at the bottom. You don't have to do it this way, but it's the way that I was thinking of it. I wanted to figure out delta I, because my average rate is my change in y over change in x. My y variable is, or my dependent variable is I, so delta I over delta x is going to be my average rate of change. And so the change from 100 to 3787 is 3687. My change in x is just 1 year, because I'm measuring x in years. And my initial value, which I'll need for later, is that 100. And so my average rate is $86.87 per year, at least within the first year. That's my average rate of change. And my relative rate in that first year is going to be my average rate divided by my initial value. So it's you can either look at it as my delta I over delta x divided by my initial value, or delta I over my initial value all divided by delta x. Either way, you should get 36.87, or over 3,000%, almost 3,700% relative rate of change. Now, for the average rate of change for the next year, going from year 1 to year 2, we see that we've increased by a lot more. My delta x has stayed the same, so my average rate has increased quite significantly, which kind of matches what we saw for the behavior of the graph, that the slope keeps getting bigger and bigger. The relative rate, though, if I take, let's see, 139,655 and divide that by my initial value, 3787, I get 36.88. So it was approximately constant from 1 year to the next. So yeah, 36.87, 36.88. So while the average rate of change for my exponential keeps increasing, the relative rate of change should roughly stay the same. Now, let's go to this particular checkpoint was fairly quick, at least for me on my calculator. I just used the letter E. Though sometimes you can do like the inverse function of down here. So e to the x. So if I do 0 e to the x, that gives me 1. And if I do 1 and e to the 1 gives me 2.718. So there's different ways of finding that value for e. Just make sure that you're familiar with your calculator. And then if I had 10 to the x is equal to 1,000, I would have 1,000 and take the log, which gives me 3. And if I had 1,000 and I wanted to find the exponent on e, that would give me 1,000. Then I'd take the log of 1,000, which gives me 6.9, well, approximately 6.908, and so on. So that's just making sure that you know how to use those. And the last checkpoint, I've filled in most of this, but I wanted to leave a couple of them. So finish filling in the table. This is going between the growth rate, reproductive, and continuous rate. What would be interesting, which I haven't gone over explicitly, is this right here. If I start with the continuous rate, how do I get to the reproductive rate? Well, my coefficient is going to stay the same. Here, let me zoom in a bit. So it's 1 times 10 to the minus 7. And then I have e to the minus 2 times t, or minus 0.2 times t. I'm going to kind of split this up. E to the minus 0.2 all to the power of t. So I have 1 times 10 to the minus 7. And then if I do my, for my calculator, let's clear all this. And then I do negative 0.2. and then I do e to the x. That gives me 0.8187. So let's call that 0.82. So 0.82 to the power of t. And then I can get the growth rate fairly easily. That's going to be, so 1 times 10 to the minus 7, and then multiplied by 1 minus 0.18 to the t. I mean, it's approximately, because I rounded it earlier. For the other ones, identifying growth and decay, the yellow should be growth, and the orange should be decay. So whenever you see a continuous rate, here's a continuous, here's a continuous, here's a continuous, it's decay when it's negative, it's growth when it's positive. And in this case, you have a 100% growth rate, so don't be confused by that one. When you have the growth rate version, that would be this one, that one, and that one. It's growing when you are adding a certain relative proportion, and it's decaying when you're subtracting. And for the last ones, when we look at the reproductive rate, it's growing when it's greater than 1, and it's decaying when it's less than 1. By the way, that doesn't go negative. We don't use the negative exponentials, at least not in this course. Or like -1 to the power of n, because that flips back and forth across the axis. Yeah, anyways, so that is all of the checkpoints. And yeah, feel free to ask questions. Thanks.